Welcome and thank you for standing by. Today's call is being recorded. If you have any objections, you may disconnect at this time. All participants are in listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 to ask a question. I would now like to turn the conference over to Stephanie Schierholz. Thank you. You may begin.
Good afternoon. Thank you for joining us. I'm Stephanie Schierholz from NASA's Office of Communications. Today we're going to talk with experts about science investigations and technology demonstrations that will launch to the International Space Station on Northrop Grumman's 16th Commercial Resupply Services mission. The Antares rocket with the Cygnus spacecraft atop and the science inside is targeted for liftoff on Tuesday, August 10th from the Mid-Atlantic Regional Spaceport Pad 0A at NASA's Wallops Flight Facility on Wallops Island, Virginia. A 5-minute launch window will open at approximately 5:56 p.m. Eastern Time. Northrop Grumman is scheduled to deliver more than 8,200 pounds of cargo to the orbiting laboratory, including critical supplies to directly support dozens of the more than 250 science and research investigations that will occur during Expedition 65. Here to talk with us about some of the research and operations the Expedition 65 crew will support during their mission are David Brady, Associate Program Scientist for the International Space Station Program at Johnson Space Center, who will discuss the status of the Space Station Science Mission. Michael Snyder, Chief Technology Officer at Redwire, who will discuss the Redwire Regolith Print study, which demonstrates 3D printing in space using a material simulating rock and soil found on the surfaces of planetary bodies such as the moon. Dr. Ngan Huang, Assistant Professor of Cardiothoracic Surgery at Stanford University and Principal Investigator of the Cardinal Muscle investigation to evaluate whether engineered human muscle cells cultured in microgravity are a valid model for studying muscle loss. Michael Salopek of Johnson Space Center, co-investigator, will talk about a new spacecraft carbon dioxide removal technology that could help future explorers on the Moon and Mars breathe more easily. He is joined by Donnie McCaghren, project manager at NASA's Marshall Space Flight Center in Huntsville, Alabama. Dr. Audrey Dussutour, Director of Research at the French National Center for Scientific Research, CNRS, is a slime mold specialist and the principal investigator of Blob, a CNES French Space Agency educational project in partnership with CNRS and ESA, which will allow students to see how slime mold behavior is affected by microgravity. Issam Mudawar, director of the Purdue University Boiling and Two-Phase Flow Laboratory and principal investigator of the Flow Boiling and Condensation Experiment, known as FBCE, will discuss the importance of this physics technology for future missions to the Moon and Mars. And he is joined by Nancy Hall, the project manager of the FBCE. Dr. Alexandre Martin, professor of mechanical engineering at the University of Kentucky and principal investigator of CRAPE, and John Schmidt, mechanical engineering graduate student at the University of Kentucky. CRAPE will test an affordable thermal protection system, also known as a heat shield, deploying when Cygnus re-enters the atmosphere at the conclusion of its mission. Our speakers will provide a brief overview of the research, and we will open the lines for a few questions after the introduction to each investigation. If we have time at the end, we will open up lines for additional questions. Your phones are on mute now. To get into the question queue, you can press star 1 on your phone at any time. The operator or I will call on you and open your mic so you can ask your question. We do ask that you stick to one question, and then, as mentioned, if we have time, we'll allow reporters to ask a second question. After we conclude today's telecon, about 1 hour later, you can listen to a replay of this teleconference by dialing 203-369-3840, and the passcode is 90662. Again, that number is 203-369-3840, and passcode 90662. It will also be available on the YouTube link on nasa.gov/live, where it's broadcasting currently. So to start, let's hear from David Brady. our Associate Program Scientist for the International Space Station Program.
Thank you, Stephanie. Thank you all for being here today. Let's just be honest, I'm the warm-up act for the main event, which is to hear our researchers share their stories in their own words. But before we do that, I'd like to provide some perspective on what it means to utilize this low Earth orbit platform that we call the International Space Station. I think you know that at NASA, we're dedicated to continuous improvement. We work hard to continually increase the value of our stakeholders' investment and return benefits for all of humanity. We do this as a team by creating tangible returns, by advancing scientific and technical knowledge, by fostering economic opportunity, and also by advancing our capability to extend humankind into the cosmos. I'm happy to report, too, though, that this agency isn't just about the big goals as a team, but we also support our individual employees with continuous improvement. And so as part of that, last week, in order to maintain and improve my scientific and technical skills, I was in a training course called Human Exploration of the Outer Solar System and Beyond. And I was taking this not only for my skills and knowledge, but also to try and broaden my perspective, because I'm thinking, you know, what is a guy like me who supports a low Earth orbit platform here have in common with these folks that are talking about very, you know, in a lot of cases, highly speculative technology stuff that hasn't been demonstrated, stuff that's still at the conceptual phase, that is literally reaching out, you know, billions and trillions of miles from Earth. I said, I mean, what can the connection possibly be? But this will still be an interesting course. And it was an interesting course. But what I figured out was that as we went through the material, as we went through systems, as we went through mission design, as we went through different things, including Einstein's field equation for general relativity, what I noticed about the material was that at least 50 to 75% of the time when they were talking about we're going to need this to explore the outer solar system or the next star system, 50 to 75% of the time there was something on space station working on that very problem. And it may not have been something for interstellar exploration like propulsion system, but it certainly was necessary for moving out not just to the local area, but beyond that. So what I'd like for you to do is, while you're listening to the researchers today talk about their experiments and talk about technology development, fundamental science, and creating benefits for humanity, is realize that even though that those targets that we seek, that you see in, you know, the science fiction stories and stuff like that, may seem a long ways away, the space station is a critical stepping stone, not only to the moon and Mars, but to the stars. In other words, the space station is the first stage of a multi-stage rocket that humanity is using to explore the universe. And that just excites the heck out of me to think about that, because our chief scientist said it well a few weeks ago when he said that a lot of space programs are looked at due to government funding as we run our program, we get our objectives, we shut down, we do our lessons learned, and we're done. I don't look at the space station that way. The space station is a stepping stone that will take us to other places as well as helping people on Earth. So thank you so much for being here today.
Thanks, David. That's a great way to consider it, and a great introduction to our first researcher, who is Michael Snyder, the Chief Technology Officer at Redwire, and he's going to discuss the Redwire Regolith Print study for demonstrating 3D printing in space using a material simulating rock and soil found on the surfaces of planetary bodies, such as the moon. Mr. Snyder, over to you.
Thanks so much. It's great to be here. I'm really excited about all the science going up. I'm really happy that we're part of it. The Redwire Regolith Print project is a tech demo of on-orbit additive manufacturing using regolith simulant feedstock material. This represents a critical step in developing sustainable manufacturing capabilities for the lunar surface that will ultimately establish a permanent human presence off Earth by utilizing available resources with adaptive systems. So really exciting for the future, and hopefully we get, something like this is a derivative that gets eventually deployed to the moon. For this demonstration, an initial set of 3 specimens will be produced on the ISS. That's going to be done by installing newly developed regolith manufacturing components into Redwire's existing additive manufacturing facility. Once those components or specimens are returned to Earth, NASA will test them, test the material properties of the print by performing destructive tests on the specimens. The capability has already been proven on Earth, but requires some further validation in the space environment. Operating both on the ground and in microgravity would increase the confidence in the process for use on planetary bodies with gravity fields weaker than Earth's, including the Moon and Mars. The regolith print demonstration will be the first ever test of manufacturing with regolith simulant feedstock in space. The hardware was developed in partnership with NASA's Marshall Spaceflight Center and was created to identify and test the methodology for regolith manufacturing that can be used on the lunar surface to support the Artemis program. A key phase of NASA's Artemis plan is creating lunar infrastructure for future exploration missions to the surface. This foundational infrastructure is critical to humanity's sustainable presence on the moon and beyond. This payload is practically a manufacturing head that we'll just insert into our existing additive manufacturing facility, as previously mentioned. We've had that facility on ISS since 2016. We produced over 200 tools for it. So this is just basically a new deposition head and a new deposition plate that we'll be printing on. And we're really excited about this because this is the first time the additive manufacturing facility will be used as a research platform to test a new manufacturing technique and not a part in microgravity. So with that, I'll open it up for questions.
Great. Thank you for that wonderful introduction, Michael. So as a reminder, press *1 to get into the question queue, and we'll go through the questions. So first up is Robert Perlman from Collect Space.
Hi, thanks. Michael, you just mentioned that you'll be producing 3 different specimens. What exactly are you printing or creating? Is it bricks of regolith, or what's the product that you're going to be testing through this? And is there a significant difference between using regolith as an additive material in microgravity versus a 1/6 gravity environment?
Yeah, so that's a great question. Great to hear from you. It's been a while since we've chatted. So I'll go backwards to forwards on that. So we're trying to figure out what the difference is between 0G and 1G, and if there is no difference, the odds are we can extrapolate the data and show that there won't be any in the 1/6 environment. However, if there are differences, then we're going to have to kind of reevaluate or create more samples to understand what those differences are and what kind of design tolerances we'll need to incorporate for future lunar activity. In terms of what we're printing, we're basically going to maximize the science possible by building a bunch of plates, layers of material, so that way we can bring them back down to Earth and form them to the exact specifications of the test specimens and produce as many of them as possible to do the actual destructive testing.
Okay, thank you for that. Our next question comes from Jeff Faust.
Yeah, good afternoon. I'm just curious about what simulant material you're using. Is this sort of lunar simulant like JSC1 or something you've come up on your own?
Yeah, so this the feedstock material is JSC1A and also a binder.
Thanks.
Thank you. The next question is from Madeline Pryor of 3D Native. Madeline, you can go ahead.
Hi, sorry, I was muted, I didn't realize. So actually my first question was about the material, so thank you. My second question was, in terms of technology, is this more of an FDM method, or what kind of technology for the 3D printing are you using?
Yeah, it's extrusion base that's similar. It's similar to fused deposition.
Okay, thank you.
Okay, those are the questions in the queue. I do have one question for you, Michael. What are the roots of this study? I think you had referenced the NASA Centennial Challenge. Can you tell us a little bit more about the path to get here?
Yeah, so we've been kind of playing with regolith and regolith with regolith simulant and regolith simulant with binders, through what we're doing in this demonstration all the way up to centering for quite some time now. We did participate in the first round of the Centennial Challenge. That's kind of where the genesis of the material came from, and we have a great support at Marshall Space Flight Center and turning what existing hardware we have up there and utilize it fully. So it's taking the AMF, which has been up there for some time and also developed with Marshall, and utilizing it further. So we took something that we developed with our own R&D with something that we have up there and combined it in this project that can hopefully benefit the Artemis program.
Okay, fantastic. And one more question from Janet Heaton at the Virginia Spaceflight Academy.
Hi there. So I'm Janet, and we have a question from Elliot, who's one of our campers. He's 13 years old, and he's asking, as far as 3D printing infrastructures on the moon or Mars, what kind of concern is it for the temperature?
Elliot, that is an excellent question. Temperature is extremely important, especially on the lunar surface, because the temperature fluctuates so much. So we've developed a few different binders to work with this system. The first one that we're utilizing is a little lower temperature, which can be fine as long as it's buried a little bit or insulated, all the way up to a binder that can survive a lunar day fully exposed without any problems. But it is extremely important to take temperature concerns in with anything you do in space, because it's a really volatile and extreme environment.
Thank you.
Thank you. That's a great question from Elliot. I thought I saw Madeline back in the queue, but maybe her question was answered. Madeline, if you accidentally got in or out of the queue, please feel free to dial *1 to get back in. And I'll take this moment to remind reporters on the line that we do have great photos and videos available from our scientists and researchers in our feature stories, so you can use those in your stories when you write them. So we will move on. Thank you, Michael, for all of that great information. And next we will hear from Dr. Nan Huang, our Assistant Professor of Cardiothoracic Surgery at Stanford University, who is the Principal Investigator of the Veterans Affairs Palo Alto Healthcare System and the Cardinal Muscle investigation on this mission. I'll turn it over to you, Dr. Huang.
Hi, good morning and good afternoon, depending on where you are. Thank you for having me. So the goal of this experiment is to study if microgravity can accelerate that process of sarcopenia, which is essentially an age-related muscle wasting syndrome. Now, we know that on Earth, skeletal muscle normally declines in their mass with aging over the course of several decades, starting as early from the age of 30 years old. But because the process is extremely slow and it takes several decades to take place, it's very difficult to test the efficacy of different kinds of drugs that could be used to treat sarcopenia on Earth. And because of that, and that's because these studies may take decades to perform and can be very expensive, microgravity has been shown to accelerate many disease processes. So we wondered whether or not microgravity may be able to accelerate the process of sarcopenia. And if this hypothesis is true, it would mean that microgravity could be used as essentially a platform for potential drug screening. Now, in our lab, we have been engineering skeletal muscle for some time, but they were used primarily for treating traumatic muscle injuries. And so we thought that maybe our engineered muscle platform could be applied towards studying sarcopenia and microgravity. The first part of our studies will be to determine if microgravity can essentially coax our engineered muscles to resemble specific characteristics of sarcopenia, and those characteristics can include having impaired ability to form new muscle, as well as having essentially a genetic signature that resembles that of sarcopenia muscle on Earth. So on both orbit and on ground, our engineered muscles will be stimulated to form myotubes, which are essentially primitive muscle fibers. and we will compare the quality of those primitive muscle fibers as well as their genetic signature between the orbit and ground samples. The other part of our studies is to try to validate this platform as a drug screening platform, using drugs that we already know to have some ability to improve muscle formation. And we'll use these drugs to see if they work as efficiently or more effectively in microgravity compared to gravity. And this work is done in collaboration with our implementation partner, Bioserve Space Technologies. And I'll be happy to take your questions.
Okay, thank you for that excellent description. Again, if you'd like to get into the question queue, please dial *1 while we give folks a moment to do that. Could you tell us why sarcopenia is a good syndrome to study using microgravity?
Sure. We think it's a good one to study because on Earth, it's something that takes decades to progress. And so if it could be accelerated to a matter of like weeks, on orbit, then that would dramatically accelerate the process of being able to screen drugs that could be potentially used to combat sarcopenia on Earth, as well as maybe have benefits for our astronauts on orbit as well.
Okay, great. And we do have a question from Ben Johnson of Nature Medicine.
Hi, thanks very much. I'm interested if the model works and the cell grows, you'll be testing kind of drugs that have already been approved, perhaps for other conditions, and is the idea that you can then test these drugs on astronauts to combat the muscle loss seen there?
Yes, and so we designed this to have multiple functions, both for civilians on Earth as well as our astronauts on orbit. Currently, we're using drugs that are not, as you know, there are no clinically approved or FDA-approved drugs for treating sarcopenia right now. And most of the drugs that we are using are those that have been shown in some, preclinical studies to have some benefit, but are not, commercially available or FDA approved right now for this indication. But yes, that would be the general goal, that we can find ways to treat muscle wasting in both on Earthlings as well as in our astronauts.
Okay, fantastic. Thank you. Our next question is from Max Leafy of Wired.
Hi, thank you. My question is, how much does it matter whether the mechanism of muscle loss or sarcopenia is the same whether you're seeing it in microgravity or on Earth?
So I guess we don't really know if the actual mechanism in terms of the progression or the mechanism in that case is as important. But we ultimately care about the end result, which is, do they experience characteristics of muscle wasting. In this case, we're specifically looking at, their impaired ability to form muscle myotubes. And that's really just only one specific characteristic that we can do in our experiments. And that's why we're hoping that, by looking also at their genetic signature, which, can be much more molecular and cell-based, we can, get a better, insight and more details to know whether or not microgravity is essentially leading to that same result of sarcopenia, regardless of what the mechanism would be.
Got it. Thank you.
Thank you. And our next question is from Amy Thompson from space.com.
Hi, thank you so much for taking my question. I was just kind of wondering a little bit of how the experiment is going to work. Like, are you using tissue chips? How long is it going to run for? That type of thing.
Sure. Well, thanks for asking some of these details. So we are essentially using a tissue chip system where we create engineered muscle that are composed of muscle progenitor cells that are growing on scaffolds that basically cause the muscle, the primitive muscle fibers called myotubes, to organize in parallel the way, in general, our skeletal muscle in our body are organized. And these experiments are going to be conducted over the course of 7 days. So once they reach orbit, they will be stimulated with a kind of media that would normally coax them to form these primitive myofibers. And we will then, look at different time points, the formation of those myofibers. And then at up to a week, we will then preserve the samples so that we can study them back on Earth to look at their genetic and protein signatures.
Okay, fantastic. Thank you very much, Dr. Huang. We'll move on to our next subject at this time. So next up, we have Michael Salopek of Johnson Space Center, who's the co-investigator for the 4-bed CO2 scrubber. He's been working at Johnson Space Center since 2007, starting out in flight operations for the Space Shuttle and then moved to flight operations for the Space Station in 2010. And he started in the ISS Program Office in 2018 and has served as the ISS Vehicle Integration Manager for this investigation since then. And also available to answer questions is Donnie McCaghren, the project manager at NASA's Marshall Space Flight Center in Huntsville, Alabama. And he has worked at NASA as an engineer and project manager for 31 years and has served as the 4-bed CO2 scrubber, I'm missing a word, project sponsor, I think, for the last 4 years. So I'll first hand it over to Michael, and both Michael and Donnie McCaghren are available to answer questions as well. So let's start with you, Michael.
Hey, good afternoon, everyone. So the 4-bed CO2 scrubber is essentially a next generation design iteration of the current onboard ISS CO2 scrubber, and that's been operating on board for almost 20 years now. And what we did was we used data gathered over those 20 years with failure modes and other lessons learned, and the Marshall team was able to go identify multiple design changes in order to improve the reliability of the components of that system, eliminate a lot of the previous failure modes that we've seen over the course of the legacy systems operation, and then of course to improve the CO2 removal performance as well. And each of those items are extremely important for building future exploration class life support systems, with spare mass being very important, and also we wanted to provide a lower CO2 level environment for future crews to improve their health and well-being as well. So the overall goal of 4-bed CO2 when it's on orbit is to demonstrate this improved reliability of the design changes. We're going to trend the long-term CO2 performance data. What we've seen in legacy systems is the ISS atmosphere may degrade some of the removal media over time, or other contaminants that are only kind of exist in the ISS atmosphere have gotten introduced, and we've had challenges that in the past. And then finally, we're going to also, we have the ability to sample the product CO2 that is removed before we vent it overboard, and we return that to the ground for analysis, and we're using that to verify its purity to be used in the future carbon dioxide reduction system. So if 4-bed successfully meets all those demonstration objectives, we do plan on integrating it with the Sabatier CO2 reduction system, and that system itself allows us to further close the loop on water recycling, but it does require very high purity CO2. And, the other neat thing about this project, to kind of echo David's introduction, is that, 4-bed really underscores the importance of ISS in developing these technologies and techniques to go beyond low Earth orbit, both with the historical data that we gathered to do these design changes, and of course we plan on doing on orbit with the technology demonstration once it launches. I'll turn it over to Donnie. I think he wants to say a couple of words talking about the Marshall project side of the house.
Hey, Mike. Good afternoon, and everybody else. Good afternoon as well. Thank you, Mike. That was a very good lead-in. Some of the things that Marshall has integrated into the 4-bed CO2 system, as Mike mentioned, there were multiple failure modes that have been studied over the history of CO2 removal on orbit. We have added an externally accessible removable filter in the event that we have any FOD or dust that gathers in our system. We'd be able to clean that. That was one of the failure modes that we addressed. We did an extensive study and selected stronger, more thermally stable sorbent materials to be used in the system. So we plan to be much more efficient at absorbing the CO2 and being able to get rid of the CO2 on orbit. We also incorporated a new valve design, which is a much more FOD tolerant, if you will. Again, if we have dusting issues in our system, the valve has been proven and tested to be more FOD tolerant. And so those are just a few of the design features that we've incorporated, and we are very excited to deliver this hardware to station. And based on the performance that we have seen on the ground, we're getting very good performance out of the hardware, and we're very excited to see what it can do on orbit. And then with that said, I'll leave it at that for now, and then we will entertain questions if there are such.
Great. The wrong folks can press *1 to get into the queue to ask a question. I'm curious if you mentioned you use better materials. Oh, were those tested on the ground, or were any of them tested in orbit?
So a lot of the materials that were tested, I think there were some 14 to 15 materials. I was not involved in the project at that point, but I did do some research on the study that was conducted there at Marshall. There was numerous materials tested, and they were tested on the ground. Now, obviously, we have history with the materials that have been used on orbit, and the materials that have been selected for this project are much more, as I mentioned, stronger, more thermally stable, more efficient at absorbing the CO2.
Great. And we do have a question from Robert Perlman of Collect Space.
Hi. For this demonstration, will this be used in place of or in addendum to the systems that are already on board for scrubbing carbon dioxide? And how long will it be up and running? How long does the test occur?
Yeah, that's a good question. So we do plan on running it side by side with the existing systems. There's another technology demonstration that's up there that launched 2 years ago called the thermal amine scrubber. We actually plan on running that and 4-bed CO2 side by side, and that will allow us to control the ISS carbon dioxide levels lower than the legacy systems can provide. The legacy systems will still remain installed, and we're actually one of the things we're doing is augmenting the ISS CO2 removal capability with this technology demonstration, which allows us to control to lower levels, even with the larger crew sizes we can expect on orbit. As far as the demonstration period, the initial demonstration period is 1 year, where we're going to be taking multiple of those CO2 samples to return to the ground and just kind of using that as our shakeout time frame, and then from there it'll remain installed for at least 3 more years so we can gather long-term reliability and performance trending data. The schedule for it perhaps being integrated into that future carbon dioxide reduction system, that's 2 or 3 years down the road, I believe. So we have some more time to gather supplemental data to determine the right technology to integrate with that system.
Great, thank you. And the next question is from Amy Thompson. I thought we had a question from Amy Thompson. Maybe not. My apologies. Can you elaborate a little bit more about the design aspects that will make it better for missions beyond low Earth orbit?
Yeah, I mean, I can weigh in a little bit on that. So from one of and Donnie kind of mentioned about the valves. So one of the challenges that we had with the old system was that these valves would fail every year or so. Dust would get built up into them, things like that. And we would have to maintain a steady supply chain of delivering new valves to ISS to replace the failed ones in the system. Obviously, that's not acceptable for low Earth orbit. So what the Marshall team did is they took a really neat and novel approach to allow these valves to be easily removed from the system and then taken apart on orbit, cleaned and reassembled and placed back into the system. So that reduces the need to have a constant supply chain. We only would need to carry a couple of spares on board. And the filters Donnie mentioned as well, the way we had to manage that with the legacy system is we'd have to remove an entire bed, which is it's about half the size of the system. It's probably about 100 pounds of the system, and replace those periodically as well. Now that can be accomplished by just removing a filter and cleaning that on orbit. So those are two of, I think, the major design changes that we implemented to really help align with the way we would have to maintain spares and be able to conduct repairs for missions beyond low Earth orbit.
Thank you. And the next question is from David Curley at the Discovery Channel.
Thank you. This sounds evolutionary, not revolutionary. Some material change, not really massive design changes. Have I got that right?
I think for the most part that's very accurate. It's evolutionary. We've learned a lot from the heritage systems that have been on orbit, and we've tried to incorporate lessons learned from that. And hopefully Mike will agree with that statement. We do anticipate that we would use less power and obviously be more efficient. We might be able to get by with a distributed system and those kinds of things. So this whole technology is leaning itself hopefully toward exploration or affecting what we do with exploration.
Okay, thank you.
Yep, I would agree with that, Donnie.
Even better. Great, thanks, Michael. Okay, we'll move on now to our next investigation. We have Dr. Audrey Dussutour, Director of Research at the French National Center for Scientific Research, and she is our slime mold specialist. She's a slime mold expert and actively involved in science communication by means of books, movies, radio shows, conferences, and is the principal investigator of the project Raise Your Own Blob, involving ESA's French astronaut Thomas Pesquet and 5,000 schools. So I will hand it over to you to tell us more about this fascinating investigation.
Hello, everyone. Thank you for having me today. So I'm quite excited to talk about our project, Raise Your Own Blob. So I'm a PI on this project, but you have to know that it involves a lot of people, incredible people that couldn't be here today. So myself, I'm a biologist, and I study slime mold behavior. So our project called Raise Your Own Blob is coordinated by the National Center for Spatial Studies, called the CNES in French, the European Space Agency, and the French National Center for Scientific Research. So the aim of the project is to raise slime molds aboard the International Space Station, but also, which is quite exciting, in 5,000 schools on Earth. So I don't know if you know, but slime molds are unicellular organisms, but they can reach few meters square. So this organism, in fact, double size every day, and they demonstrate quite complex behavior, such as learning and memory. So yes, you heard me well. We are just sending into space a smart organism that grows exponentially. So our aim is to investigate the effect, of course, of microgravity on slime mold behavior, especially exploration behavior, but also growth. But the real main objective of this project is to engage kids in interesting and exciting scientific experiments. And so they will be able to compare their results with the one obtained by the famous French astronaut Thomas Pesquet. So I really hope you will motivate them to do a scientific career. So thank you for your attention, and I'm open to questions.
Great. As a reminder, please press *1 to get in the question queue. Excuse me. And I know that we have images of this slime blob on our website as well, so you can use those. Can you tell us how long the investigation will run if it is doubling in size every day? How many days are we talking about?
7 days. Only 7 days, and we are setting very, very small slime molds.
Okay. I'm sure the astronauts will be pleased to hear that. Okay, so if folks can press *1 to get into the question queue. In the meantime, can you tell us a little bit more about how you got involved in this project?
So it was by chance, actually. I gave a big conference at the CNES, so the Center for Spatial Studies, and they didn't know about slime mold at the beginning, and then when they heard about these organisms, they thought it was perfect to rear them in the International Space Station, but also in schools. So it was a kind of easy experiment to run by kids. So it's how it started at the beginning.
That's great. And we have a question from Amy Thompson of Space.com.
Hi, thanks for taking my question. I was wondering if you could talk a little bit about Thomas' role in this and what he's going to be doing with the slime molds, and then how the kids are going to be interacting as well. Thank you.
Thank you. So, in fact, the main mission of Thomas Pesquet is to revive the slime molds because we are sending them in a dormant state. So the experiment is already set up in a little box, but Thomas has to inject water in the system so the slime mold will wake up. Because we didn't send, of course, slime molds living at the International Space Station. We wanted to control when we will wake them up. So just a droplet of water, in fact, is enough. And we know that after 7 days, they will kind of sleep. And we are recording the experiment with an automatic computer and camera connected inside the box. So in fact, really, the role of Thomas is to revive the slime mold, which is the most important part, actually. And after he will interact with the kids by giving an interview and by sending his results to the school. So when we will start the experiment with the kids, we will already have the results of Thomas.
Great, thank you. So at the conclusion of the 7 days, does Thomas actually have to do something to make the experiment conclude as well?
No, in fact, the slime molds are doing everything by themselves, actually, because we didn't provide them so much food in the experiment, the slime molds, when we tested it on Earth. As the slime molds, in fact, after 5 to 6 days, they go back to dormant stage because they are hungry. And when slime molds are hungry and under stress, they're really actually going to a dormant stage by themselves. So, in fact, the slime molds will run the experiment by themselves.
Okay, great. And are there intentions to bring this experiment back to Earth, or will it stay on the space station?
No, it would stay at the International Station.
Okay, great. Well, I don't see any other questions at the moment in the queue, but maybe everybody is just processing the idea of the slime mold living on the space station. So we'll move on and potentially come back for more questions later. Thank you very much. That was very fascinating. So next we have Issam Mudawar. He's the director of the Purdue University Boiling and Two-Phase Flow Laboratory and principal investigator for that research. Also available is Nancy Hall, the project manager for FBCE. Nancy is a research scientist and project manager who's been working at NASA's Glenn Research Center in Cleveland, Ohio for more than 30 years. And has managed International Space Station experiments that studied the behavior of polymers, magnetic fluids, liquid crystals, and two-phase flow systems in a reduced gravity environment. This is a biological physical sciences investigation and also has to do with heat, which was a topic asked earlier. So I'll hand it over to you, Dr. Mudawar, and if you can tell us more about the flow, boiling, and condensation experiment, please.
Thank you very much. The flow boiling and condensation experiment, FBCE for short, it will serve as the primary platform for obtaining two-phase flow and heat transfer data in microgravity on the International Space Station. Now, that is for use by the fluid physics community at large rather than a single team. I would add that it is the most capable fluid physics science facility developed by NASA for microgravity to date. Now, it will impact several space applications, including first, space vehicles for missions to the Moon, Mars, and beyond, including those using nuclear fission. Second, the vapor compression heat pumps for temperature control in planetary bases on the Moon and Mars, for example. Third, thermal control systems and advanced life support systems inside the spacecraft. And fourth, the cryogenic systems, such as those used in nuclear thermal propulsion and proposed fuel depots. Now, the ultimate deliverable from the current project, which is the first in a series, will be experimental data and high-speed video images that will enable formulation of empirical, theoretical, and computational models for both flow boiling and flow condensation, which are, these models, which are essential for design of not only space systems, but numerous terrestrial energy systems as well. And Nancy Hall, the project manager, may have also some additional information regarding the facility as a whole.
Thanks, Professor Mudawar. Yeah, the facility the experiment is going into is called the Fluids Integration Rack. And what it consists of is a large optics bench platform that allows us to integrate mini facilities in there. So what that does is it allows us to configure the rack to our specific needs, and that's basically what we're going to be doing with it. The experiment that was in there is being removed, and we will be integrating the flow boiling and condensation experiment mini facility, and then utilizing the interfaces of the facility and station to condition the fluid, provide power, provide data, and downlink all that information. So at this time, yeah, we welcome questions.
Fantastic, thanks. And again, *1 to get into the question queue. We'll ask a similar question to some that have been asked already, which is, what kind of support is needed from the crew members on the space station, and how long, what is the demonstration period for this investigation?
It will be operated from the ground, as a matter of fact, but initial installation, obviously, into the fluid integrated rack that Nancy mentioned will require some effort by the astronauts. Once it's ready, we're talking about probably a few weeks of testing to get the first data. Now, the system involves different modules, plug-in modules. So we test the first module, we get our own data, and we begin the analysis. Following that, the National Science Foundation has already set up projects to utilize the same module and get data for other teams. Okay, and when that is accomplished, then we switch to a different module altogether. We get our data and we do the analysis, then the facility or the module will be available for a National Science Foundation team to do the same. And we keep going in that fashion.
Okay, thank you for that explanation. That's very helpful. Nancy, you've managed several International Space Station experiments. Is there anything that makes this one particularly unique from the others that you've managed?
Yes. This one is probably the largest one I've managed. A lot of the other ones were smaller. It went in a different facility, and it was also led by a contracted team, so I was providing oversight. This one's also unique in that it was done in-house, and what that means is it was actually done by NASA civil servants. We had engineering technician and some support staff. So for NASA Glenn, we had quite a bit of, like I mentioned, NASA civil servants working on it. So managing a large group of personnel was both challenging and fun. And like I said, it was exciting when we got everything together, finished testing, and got it ready to out the door. And now everyone's looking forward to seeing it launched.
That's great. And when you say larger, do you mean physically in size larger?
Yes, physically inside, and also just complex, because the other experiments went in the microgravity science glove box. So we were just using maybe half the size of what this facility is. So yeah, larger in size and also larger in complexity.
And so can you give us a sense of how big it is?
Yes, basically this is the equivalent of what we would call a full-size rack. If you look at the station from the floor to the ceiling, although you have to be careful saying, top and bottom, because there's no up and down in space, but the facility basically takes the whole length of that, this experiment takes the whole length of that facility to go in there.
Okay, fascinating. And what are some of the challenges of creating a two-phase system instead of one phase? I'm not sure if that's a better question for Dr. Mudawar or Nancy.
Yeah, let me try to answer that question. Now, the successful implementation of flow boiling and condensation, the way I described them, relies on the ability to reduce system weight and volume. These are primary goals. Now, these reductions are possible via the orders of magnitude enhancement that you could get in heat transfer processes in systems utilizing flow boiling and flow condensation as compared to present systems that utilize only pure liquids, okay? However, The implementation will require a very thorough understanding of how these heat transfer modes are influenced by reduced gravity. The way the vapor separates from the liquid is very different on Earth, for example, compared to the Moon, compared to Mars, and compared to zero gravity.
Okay, and what future NASA space systems may be impacted by this experiment?
Yeah, as I mentioned earlier, you're talking about missions to the Moon, Mars, and even beyond. We're talking about the planetary bases on the Moon and Mars, developing the temperature control for those, also the thermal control and life support systems within the spacecraft themselves, and also cryogenic systems. There's a variety of those.
Okay, fantastic. Thank you so much for that really interesting information about this investigation. We appreciate your descriptions. We'll go ahead and move on to our next investigation, which is the last one we're talking about today, from Dr. Alexandre Martin, Professor of Mechanical Engineering at the University of Kentucky and Principal Investigator of CRAPE, and John Schmidt, Mechanical Engineering Graduate Student at the University of Kentucky. So, Dr. Martin, if you want to get us started.
Yes, hi. So, so just to give you a little bit of perspective here, so here at the University of Kentucky, we've been working on developing computational tools for modeling heat shields. So that's been going on for about 10, 12 years now. So we've worked with NASA on trying to interpret the data from various missions in the past, Stardust, Mars Science Labs, and even most recently the latest Orion flight, so EFT-1. So one of the things that you can see with the mission we worked with over the last few years is that these are real missions. So the heat shield that was used is the one that was flown on that mission. So the data we get from that is from a heat shield that's done and validated almost at that point. So there's a kind of a need to be able to screen new material, try to develop heat shield before they're actually used on real vehicles. And that's very important to get that part done, and it's also very important from a code perspective, so software perspective, to be able to see if what we predict with our code is able to replicate the data that we get. So through some funding from NASA and NASA EPSCoR, we've decided that we were going to try to develop such a project and develop our own little capsule that could test various reentry system, and the one that we're very interested in is, of course, the heat shield. So those heat shields were developed by undergraduate students at the University of Kentucky, and then when the project got mature enough, it moved on to graduate students. So over the year, we did a couple of suborbital tests, so with sounding rocket, and now this is our first near orbital velocity test. So we're actually going to test the heat shield at real reentry speed. So the idea here, we have 3 capsules that we're sending through this Cygnus vehicle. We're gathering data on heat shields. So 2 are a material that we know very well, and 1 is an actual experimental material that's been designed and fabricated by NASA Johnson and Oak Ridge National Lab. This is a 3D printed heat shield, and I think it's the first time we're going to fly that. So our concept is very different from any other experiment that you would have on the ISS. So we're going up with the Cygnus vehicle, and then basically the astronaut will take our capsule, set it aside, and put it back in the Cygnus vehicle. And when the Cygnus vehicle is going to unberth and come back down on Earth, with all the trash, our capsules will be inside. So, of course, the Cygnus vehicle is not equipped to re-enter. It's meant to be destroyed and burned during re-entry, but our capsules are equipped with heat shields, so they will survive re-entry. So they're going to be released from the Cygnus vehicle. They're going to take data, and they're going to send the data back through the Iridium satellite network, and eventually back on Earth as well. So this is a concept. We didn't invent that. This is a concept that was proven and worked well for Aerospace Corporation, the first, I believe, that developed this system. They use this to monitor re-entry debris during breakup. So that's our goal here. Our overall goal is to keep doing this, to develop other capsules, to measure other things. So we already have another set of 3 capsules that are going to fly in a couple of years. these will take gas phase data in the shockwave in front of the vehicle and using a spectrometer. So that's our project. So if you have questions, I'll be happy to answer that. And I have John Schmidt, who's the current graduate student in charge of the project, that's online as well.
Thank you. John, do you want to say a couple words?
Yeah, I've just been in charge of building these capsules, testing them, getting them ready and qualified to be taken to the ISS, and I've just been able to learn a lot from working under Dr. Martin and being exposed to NASA.
That's excellent. Okay, well, your first question is coming from David Curley of the Discovery Channel.
Dr. Martin, could you just explain a little bit how the capsules are released? They're inside Cygnus. When Cygnus starts to burn up, they get released with everything else that's in it. How does it actually work? So they're in dormant mode. Once the ISS, essentially the astronaut will put them in dormant mode, and then there's a method that will detect reentry. So what happens, they're in a shell, aluminum shell that protects them. So when everything is falling apart and burning, exploding, these are somehow protected. And the aluminum shells are held together by essentially plastic bolts. So as the heat starts to build up, and that will happen also inside the vehicle, as the heat starts to build up, those plastic bolts are going to melt, and then the shell is going to open, and the capsule will be free to start taking data. And is there actually a UK decal on one of these?
There is a UK decal on every one, each of the capsule. We make sure of that.
So that you can find it later?
Yeah, well, we're not going to find it, but you can hope.
Okay, so it starts out inside Cygnus. It doesn't get expelled from Cygnus.
Sorry?
Great. So it starts out from inside Cygnus, the interior.
Exactly. So we're trying another concept for the next one, but it's much more complicated. But this is a safe one. Let's say that's a system that's worked in the past, so we're trying to demonstrate that we can do this. So it's inside. It's with the trash right now, and not right now, but it will be with the trash. And then when everything burns, these are meant to survive.
Great. Yeah. So right now it's with all the other science. Okay. So the next question is from Jeff House.
I wanted to ask about the capsule with the experimental material that you're testing. Can you say anything about what that material is and what the benefits it has versus the other ones using the conventional materials? Thanks.
So I cannot say anything about the composition of the material, but it's basically it's 3D printed. So it's showing off that we can 3D print a capsule. So there's a lot of benefits to just being able to show that we can do that. So I don't know exactly, again, I don't know the composition. That's Oak Ridge that would be able to answer that question if they can. But one of the goals, and that might be a long-term goal, is to be able to tailor, to very fine-tune these heat shields that you can decide if, for instance, the nose needs to be a different density of material, and the side is less dense, more porous, and things like that. So using a 3D printer, you can pre-program that. You know where your heat pulse is going to hit. You know where the temperature is going to be very high. So you can maybe change the properties of the heat shield based on what you expect to have during reentry.
Okay, thank you. The next question is from Robert Perlman, Collect Space.
Hi, you mentioned not recovering the decal. Is that because you expect it to burn off, or are you not recovering the capsules once they're in the water, presumably, or wherever they'll fall? And if you are recovering them, is there anything aboard or inside the capsules other than instrumentation that you're bringing back to Earth?
So these we're not planning on recovering them. So they're going to fall in the water somewhere in the Pacific. So there's a region that's been identified where they could fall, but I mean they're 12-inch, so there's at this point there's no they're not equipped to be recuperated. There will be a GPS on board, but I don't think we can send a boat to get them. So there's nothing on board that on these one, all the data will be stored but that's sent back. So if they survive hitting the water, which in the past has been shown that they could, and we've made some tests to make sure that ours would, they're just going to keep transmitting until the battery dies, essentially.
So in that case, is there a if found return to sender label somewhere on them if they wash up on shore someday?
We used to do that for the suborbital one, which we actually had a very good idea where they're going to fall, but I don't think I didn't think about that for these ones. Unless John, maybe you can answer that. Did you put something in there?
No, there isn't a accessible port.
Okay, and John, I think I may have cut you off earlier. Did you have something else you were going to add earlier about the experiment?
No, that's it's been a pleasure to work on this, and it's great to finally see it launch coming up.
Yeah, and then you have to wait, of course, a little while from the time that it launches until the capsule detaches and comes back. But every step is important in this process.
It's one of the rare cases where we're going to be more exciting about the re-entry of the Cygnus than the launch, I guess.
That's fantastic. Okay. Thank you. And thank you to all of our speakers today. We do have a little bit of time if there are lingering questions from any of our reporters for any of the investigators on the line. I believe everybody is still with us. So I'll give you another opportunity to dial *1 to get into the question queue. You can also ask questions of David Brady, who is also on the line, if that's more appropriate. So I see a question from Mark Carreau of Aviation Week.
Thanks. Can you just say how long the Cygnus mission is planned for? And then my real question has to do with the Redwire Regolith study. I wonder if you might be able to describe what the simulant regolith is comprised of.
And I can answer the first. Mark, we're expecting the Cygnus to stay on station into November and come back sometime in November.
Yeah, and for the simulant, it's just standard JSC1A, so it's comprised of mostly metal oxides that simulate the condition or the material on the lunar surface.
Okay, thank you. Thank you to all the reporters who have joined us on the line today and all of your fantastic questions. Thank you to all of our scientists and researchers. We know this is an exciting time for you as you prepare to send your science to the space station. You know, you've often been working on it for quite some time, and it is a great time to get it actually into space and get started. So thank you for participating today, for taking time out of your busy schedules to tell us all about your investigations that are headed to the space station, that unique microgravity environment. So, the Expedition 65 astronauts will support these as part of their 6-month science mission aboard the International Space Station and other investigations as well. As mentioned, the launch of the Northrop Grumman spacecraft is scheduled for next Tuesday, August 10th at 5:56 p.m. Eastern Time. You can follow along at nasa.gov/Northrop Grumman for regular updates in advance of the upcoming launch. And you can follow at ISS_research on Twitter to follow the science. Again, you can listen to a replay of this teleconference if you dial 203-369-3840 with a passcode of 90662. And if you think of additional questions, you can reach out to me, Stephanie Schierholz, and we'll get your questions to the researchers as appropriate. An audio recording also will be posted to the NASA Videos YouTube channel that you can access at any time. And of course, you can find the high-res images and video for download through the link in the media advisory for this telecon. Thanks again for joining us today, and have a fantastic Monday.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye.
Thank you for participating. You may disconnect at this time.